Okay, so second lecture of today. Let's see, so where were we? We have decided that this is somehow our Euler equation. By definition, it's our Euler equation. And we want to study well-posedness of this in the so-called Yudovich class, meaning that we want the vorticity to be bounded in time and L1 and bounded in space. That's the goal. And what we saw right before the break, or right before lunch, was that, when you do convolution of K with some function which sits in L1 and L infinity, you obtain something which is bounded. And I mean, if you go through the proof that I gave you and you're a bit more clever, you can actually show that convolution with something which is in, I should say here, of course, here's the F in L1 intersected L infinity. You can show that it maps functions in L1 intersected L infinity also into something which has a very nice Osgood modulus of continuity. And it's given on this form here. For r between 0 and 1, it's r times 1 minus log of r. R bigger than 1, it's simply r. And you can check that this is exactly what you want. Good. Sorry? Sorry, yeah, okay, yeah, it's fine. Good. Good. And so this is enough to sort of at least somehow hint that if you're studying well-posedness in this class, then this flow equation is well defined. Right? Because if omega belongs to this class, we expect that the velocity should be bounded and Osgood. Right? So at least this one makes sense. And I should also say, we can also check, recall, so K, the kernel is Z perpendicular, and then 2 pi absolute value of Z. And what you can check is that the divergence of K is equal to 0. I guess outside 0. So this will then imply that the velocity is divergence-free in the distributional sense. So this means that we can also see that if now these vector fields are divergence-free, we should also somehow have volume preservation. That was the theorem we saw previous lecture. Right? So if psi k is divergence-free, phi t is volume preserving. Okay, so now let's show a little lemma, which more or less now tells us that if we take a solution in this class, it is bounded by the initial data. Our solution, we have L1 sorry, this is even better. This is even equal. Okay? So the L infinity bound is obvious, right? Omega t is just to be defined to be omega naught in the inverse flow. Right? So no matter what you do, it will always be bounded by the supreme normal omega naught. Right? obvious. Now for the L1 norm, let's just check. But right, look. So the solution, we require it to be on this form. So it's the initial value and now by volume preservation, okay? So since phi is volume preserving. Okay, let's now get to the proof of uniqueness. I should have been more specific here. So I'm always I take these vector fields to be C3 and bounded, like we always did. We also want them to be divergence-free. And we want our rough path to be geometric. So, I mean, this will just be the standing assumptions for the rest of the talk. Okay? Good. Okay, so now let's prove there is at most one solution. Okay, so what we do, we take two solutions, or I mean, let's say that we have omega 1 and omega 2, which satisfies this. And let's try to show that they're the same. And omega 2 solutions. And let's look now at phi 1 and phi 2 to be their corresponding flows. Now let's define this quantity. IT, I define it to be the integral in space of the difference between the flows. Integrated against the initial condition. Okay? So let's take our flows, our vorticities, integrated against some test function, eta. All right, so we know that the first solution should be the initial value in the inverse flow, eta, minus initial value at the inverse flow. This is phi 1 inverse, and this is phi 2 inverse. Okay. Now by volume preservation, you can just sort of put this one over here. So we can write this as omega 0, and then eta in the forward flow minus eta in the second forward flow. Sorry? Yes. Just some test function. Now let's use the mean value theorem for eta so that we can bound this by the derivative of eta, so primum. And what we're left with is the integral of phi t1 of x minus phi omega naught x dx, right? And this is exactly what I called I. Okay? So why am I saying this? It's just to say that if we can show that IT is 0, we're done. That's because it means that this one will be 0. So enough to show. Okay, but now let's write it out. So recall the a priori contraction estimates. Contractive estimates gives us, let's see here, space. So this is bounded by up to some constant, the drifts. Like this. Right? And now in here, let us add and subtract. Let me get it right. So here we say subtract and add u1 s at phi 2 s. So that we get here, this is bounded by u1s phi s1 minus u1s phi 2s. And then plus. Okay, let me now write this as 1 and 2. Let's see. So now for the first, no, wait. Sorry. It's not 1 and 2 yet. Let's now integrate this one against omega naught in x dx. Can you see? I'm just integrating in space now. So, I mean, this thing is really IT as we defined it over here. And so we integrate in space. Okay, fine here. And then dx. And we do the same here. And we change the order of integration. Omega naught x dx ds. And the same here. And now let me write this as 1 and 2. Okay. Yeah, sorry about this. It's a mess. Good, but now we know that U1 is the convolution of K with something which sits in L1, L infinity. So we know that U1 is Osgood. It's Osgood regular. So we can write this as being bounded by 0 to t. Now integral over R2. And here we get the Osgood modulus of continuity. Good. Now, since we're assuming that omega naught sits in L1, this is a finite measure. And we can check, it's very easy to check, that H is concave. So we can use the Jensen's inequality. So to say that this is bounded by H of integrating exactly what's left, but exactly what's left, that's this quantity here at S. So this is IS. Okay. So now let's try to bound 2. Let me begin by writing U1 at phi 1, sorry, at phi 2, minus U2 at phi 2. Let's just write out what it is. Because U1 is the convolution now evaluated at phi 2. Oh, I should be specific about the spatial point here. This is x minus y, and integrating now the first vorticity, dy, and then minus k at phi 2, x minus y, and here we put the second vorticity. Right? But we know that the vorticity is on the form of the initial value plugged in the inverse flow. And exactly the same with the second vorticity. And now again, by volume preservation, we can just sort of interchange here. We can just put this instead of y. So we can write this as integral of k phi 2x minus phi 1y minus k of phi 2x minus phi 2y. All integrated against y. Here you mean, yes. So, or do you sometimes call it the reverse, Jensen, when it, since it's concave? Yeah. Yeah, because usually you do the convex setting, right? And then it's the opposite inequality, but take a convex function, put a minus, you get a concave, and so, yeah. Mm-hmm. Good, good. Let's see. So now I have, okay, so why is this better? Because now if I integrate this with respect to x, no, I want to do something more than this. I want to take this expression integrate with respect to omega 0 at x, and if you do this, You're left with a double integral here. Minus phi 2 of y. Okay, and now we have this integrated against initial value in x, initial value in y, and dx dy. But now let me change the integration variable again. Okay? Because here we have phi 2 of x and phi 2 of x. So I can just sort of change this one. I can put x here instead. And now I need to put phi 2 inverse of x here. Right? We can do this. It's volume preserving. Okay, but now when we're integrating this thing here, since the kernel K is symmetric, right, we can just sort of interchange the order here. We see that we're left with, what do we get? We get exactly the Osgood modulus of continuity. Exactly, okay, we need to take, so omega 0 at phi 2 inverse in the L1, L infinity norm. So now I'm just plugging in exactly the estimate that I wrote down for K. So as long as F belongs to L1, L infinity, we can get this Osgood modulus of continuity. And we already checked that if we take the initial value, we plug in the inverse flow, it's bounded by the initial value, right? It's bounded just by omega naught in L1, L infinity. That's what we just saw. Okay, and here we get h of the difference between phi 1 y minus phi 2 y, and is integrated now against like this. Okay? And now we use the reverse Jensen inequality once again. Right, so this one is just bounded by the initial data. That's what we saw. This is just the initial value, L1 intersected L infinity, and we're left with h. And exactly what do we get? So I mean, this is, of course, there's a time variable here that's, I didn't bother writing it down, but of course, everywhere there's time. And we're left with exactly is. Okay, and now you integrate all of this with respect to time. This will give you exactly the second part here, integrated with respect to time. It gives you exactly this. Integrate with respect to time. Here, and you're left with this here. Okay, so this implies that IT is bounded by right, that's what we started with here. We said it's bounded by 1 plus 2. And we can see that both 1 and 2 are bounded by the integral of h of is. And that's perfect, right? This is really the nonlinear Grunwald inequality. Okay? So since h is Osgood, this implies this is constantly equal to 0. No, you are right. Yeah, you should do it. Yeah, you're right. This is the correct, yeah, no, you're right. This is not the correct way to do it. I should really integrate first this one, then using the technical result in the beginning, and then using the, yeah, you're right. Sorry? Sorry? Yeah, I mean, up to some constant, yeah. No, because, look, I'm requiring my initial condition to be in L1. It's not 1, but I mean, it's just some constant. Sorry? You have to divide? Yeah, I mean, I'm sure you get some constant here. So, sorry, I'm not getting what you mean. Yeah, so I mean, it's just some constant, right? So what do you mean? You can define the new measure like yeah, sure. That's clear. Yes. It's just some new measure and it has finite volume, right? If omega is in L1. So then you can use Jensen. I agree there is a constant. But I mean, you can just sort of, I mean, okay, define a new measure, which is, and then you divide by the L1 norm. And then you just multiply and divide with the same thing, and you can use Jensen with respect to this measure. But, so that's certainly fine, but now let's see. So first, what did I want to do? I wanted to say integrate. So this one with respect to x, and then omega naught of y dy. Yeah, but now it should be fine, right? Because this is a function which sits in L1, L infinity. So you can say now that this is bounded by h, the difference. Okay, let me write it here. So now this should be bounded by integral from 0 to t, integral of h of phi 1 y minus phi 2 y. Right? And now this is integrated against phi naught of y dy and then ds. Right? It's fine now, right? Yeah. No, but it's a good point. And now you use Jensen with respect to this measure here. So that you get this one bounded by this. But actually, okay, so I cheated you a little bit, because what you can see, if you go through the proof of showing something like this, you will see that actually something a bit more strong is true. You can actually write k of x minus y minus k of x bar minus y times function y dy is bounded by this. It's the same proof. It's really exactly the same. And you're right. You're completely right. This is the thing that you should check. Yeah. It looks so much more nice the way I'd written, because then you immediately see that the drift velocity field is Osgood and so forth. But I was cheating you a bit. Okay. More questions? Comments? And to have somehow local Lipschitz in the initial, I don't know, probably. I didn't check. But it seems plausible, right? Up to adding and
Here you are just taking the omega naught initial data and that's the story.
yeah.
My question is that suppose the initial data is
Yeah. No, I see what you mean. Then, I don't know, could be. I mean, it seems to me like if you're adding and subtracting one term here where you sort of, then you get an additional term here, but somehow if you trace through everything, it seems like you should actually get some type of Lipschitz estimate in the initial condition. Yeah, possibly, yeah. Yes. All right. So now the only thing that's left now is to prove existence. Just leave this be here. Okay, existence. So the strategy will be, since Z is geometric, that we will smooth out the path and construct a sequence of approximating solutions. So we take some sequence of rough paths, smooth, converging to Z, and consider n minus 1. And now we want to show that this converges to what we want, to a solution. Okay, so as before, so previous lecture we proved stability of, I mean, okay, it was a linear system, but we proved stability of flows of this kind here. And we can do a similar thing here. If you go through the proof, you see you can do exactly the same thing, except you cannot really conclude immediately that the limit is a solution, right? Because it's nonlinear, right? So you need to work a bit more to see that it's actually a solution. But as before, we get equicontinuity and boundedness on compacts. And boundedness on compacts for the pair where we put phi n and phi n inverse. Okay. So the only thing is that we cannot really conclude that it converges, not immediately. Okay, but now we apply Koley. On you take on some bounded set, you can apply Koley. And this gives you, for each R, you get a converging subsequence of this pair. And then you use a diagonal argument to get some phi inverse such that let's call this new subsequence, some subsequence. This one converges to phi inverse on or in for all R. Okay, I'm skipping a few details here, but right. You can do this on each ball, and then you do counter diagonalization, and then you get something which is converging to exist this limit. Okay. And now the next thing we want to do is to prove that actually this phi is a solution of the nonlinear system. So, but the first thing we will do is we will actually define omega now to be the inverse flow. Okay? And the velocity okay, it's a bit suggestive notation, but I mean, we don't know yet that this is actually the vorticity of some equation and that this is the velocity of some equation. But it's suggestive notation, and of course, this is what we're going to prove. Okay? Then we get that omega n, which is a vorticity, because it's really the solution of this equation here. Omega n will converge to omega in L1, and un will converge to u in L infinity. This is what we'll prove. By the way, of course, I mean, I'm just assuming that we can solve this system here when you put in a smooth path. We didn't really prove this, but if you've been able to follow the lectures this far, I think it's not difficult to prove anything like this. It's not so tough. And I mean, of course, without the noise, this is classical. This is the Yudovich theorem. So, I mean, it's readily believed at least. And if you work a bit more by sort of smoothing out this kernel, you can actually prove everything from scratch. But I won't do it. I'll just suppose that we know that there exist solutions of this system here. Yeah. It's still, I mean, obviously this will still be Osgood, so yeah, sure. But I mean, you have to do a bit more work to show. It's still a nonlinear system, right? Okay. Yes.
So it's not the phi n minus 1, that's the inverse of phi n.
Yeah, yes.
Not that you are applying
Sorry, I should have said. Yeah, it's really the forward flow and the backward flow. I mean, we get, for each n, we have a forward flow and a backward flow. And just as before, we did this only in the linear case. In the linear case, we showed actually that you had convergence to a solution, but we have to work a bit more in the nonlinear case. But still, exactly the same proof works in order to get equicontinuity and boundedness on compacts of this pair, the forward and the backward flow. Okay. So let's prove this now. Right, so we want to prove first that that omega n converges to omega. Right, I mean, by definition, it's just the inverse flow. So it seems plausible, at least, that it should converge, right? Because we know that this one is converging to this. The only problem is that omega naught might not be continuous. That's the only problem. However, so for each, let's say fix epsilon, and then we can choose some epsilon naught omega epsilon 0, which is smooth, and such that it's close in the L1 norm to the initial value. Right. Okay, we can always do this. So now, let us just add and subtract lots of terms. We write this now as, now it's better to have the notes. Omega naught, Tn inverse, this is the one we started with, and let's subtract this term, so we also need to add it. Okay, and let us now subtract so we also need to add it. And finally we subtract this term. Right? For some reason I forgot to write x here. X and x. Okay? Now we integrate this in space. So we integrate this in space. So we get here. It's bounded by this one, of course, dx. Okay, let me drop this. And integrating this in space like this. Okay? Now what we're going to do? Well, we know that phi n and phi are volume preserving. I forgot to show that phi is volume preserving. I mean, we know that phi n is volume preserving because it's simply a solution of this system, right? So what you get here, this will be equal to the L1 norm of omega minus omega epsilon. Now we want to say the same here. But I didn't prove this. I didn't prove that phi itself was volume preserving, but somehow, I mean, it is the limit of something which is volume preserving, so by exactly the same argument as before, also this one is volume preserving. Sorry, okay, so we get this term here simply by changing the coordinates. This gives us omega naught epsilon minus omega naught. And this term we have to keep. Minus 1x like this, integrated dx plus. Okay. Now, since phi naught epsilon is smooth, it has compact support, we can take the limit. When we take the limit as n goes to infinity of this one, it goes to 0. You can interchange limits because, I mean, this is smooth compact support. The flow does not increase the support too much. Okay? And now we use how we chose omega naught epsilon, such that this one holds. So this implies that the limit n goes to infinity of the L1 norm is bounded by epsilon plus epsilon. Right? And now you let epsilon be small as you want. it implies the convergence. Okay? L1 convergence. Good. Okay, now let's see that we actually have L infinity convergence of the velocity. So to do this, we need a small trick. So we take some cutoff function, rho, which is equal to 1 when x is less than 1, and it's equal to 0 when x is bigger than 2, and take it to be, I don't know, smooth. Okay? And put rho delta equal to rho of x divided by delta. Now let us compare the velocity un minus the limiting, well, we don't know yet that it's a velocity, but it's limiting u. Now let's write this as k convolution with omega n minus k convolution with, well, I mean, even better. Let's write it as k convolution with omega n minus omega. Okay? And so now let us split the operator k into a singular and a non-singular parts. So one where we just multiply with k, and then we take omega n t minus omega, like this. So for this term, let's use the supremum norm here on omega n and omega. This is bounded by supremum norm of omega n and omega times the L1 norm of this guy. Right, but this guy is, the rho is cutting off. So this will be like, what will it be like? The ball around x, and then with the radius 2 delta, I guess, and then k behaves like x minus y dy, like this. Okay, just taking the supremum of the kernel. And for this term, well, here, this part is bounded. Right, all the bad things with k happens at 0. So we can take this away with 1 minus rho delta, okay, in supremum norm, and here we put the L1 norm of omega n minus omega. Yeah? Sorry, it will be. Yeah, yes, of course. Yeah. I mean, outside. Yeah, sure. Yeah. Clearly. I mean, you could even say. Yeah, even compactly supported in here. Okay. Good, so now, I mean, the L infinity norm of omega n and omega will necessarily be bounded by the initial data. So this one will be bounded by 2 times omega naught. And again, when you're integrating this, you get an integral on the form 0 to 2 delta, and then you get 1 over r, but you get r dr here, right? When you change the coordinates. And this term, well, as long as you're away from this, from 0, this guy will be bounded by 1 over delta. Right, because 1 minus rho delta, the support sits outside of the singularity. Right? Now, so taking supremum in x here now, and send n to infinity. So you take supremum in x first, and then you send n to infinity. Well, we just showed that omega n converges to omega in L1, so this will just be equal to 0 in the limit. And you're left with some constant, depending on omega naught. Omega naught in the L infinity norm times delta, right? And delta was arbitrary, so you just send it to 0, and you're done. Any questions? Okay, now we get to the final theorem. And now we show finally there exists a solution. Of Yudovich. Or, yeah, let's say, just call it star. I don't know what to call it. I mean, it is, of course, the Euler equation. But it's sort of in this Yudovich class. But let's just say there exists a solution of star. Sorry? Sorry? Yeah, sure, yeah, probably. Some constant, yeah. Yeah, that's why I wrote the twiggle. Yeah, I know there is a constant, sure. Okay, so we're ready to finalize the proof of existence now. So we already know, I mean, we know simply because we defined it, omega to be exactly the inverse flow. And we defined U to be the convolution with this kernel. The only thing that's left to check is that phi is actually the flow of this equation here. And once we've done that, we're done. Only need to check that phi is the flow. Okay, but this is also now something similar, very similar to things we've done, I don't know, 2 or 3 times now. Let's just write down the approximating solution, and let's write down the expansion of the approximating solution. So we know that the approximating solution looks like this. KL and S. Right? That is just this simple Taylor expansion type formula. Now what do we see? That this is uniformly bounded. I mean uniformly in N as one variation path right? And then we know from the a priori estimates that we can bound the remainder. Okay, now I'm writing it down explicitly. This is exactly the a priori estimate that we got for the remainder. Okay, and we know convergence, right? We use the equicontinuity to say that phi n is converging. So this term will converge, this term will converge. And if we can show that also this term is converging, then certainly all terms in the expansion converge. And so also this one must converge. And we can take the limit. Okay? But let us now just check that this one is converging to what we want it to converge to. And how do we do this? Well, again, we just add and subtract. Say we can bound this by absolute value of un at phi n minus ur at phi n. And then plus ur of phi n r minus ur of phi r dr. Right, and this one is fine. Right, we just saw that this one converges in L infinity. So this is bounded by t minus s, and then you take, or let's say like this, integral from s to t, and then supremum norm. And here you put integral from s to t, and now you use that since u is the convolution of something in L1 intersected L infinity, this is Osgood. So here you plug like this, and this one goes to 0. Right, we just showed that this one goes to 0, and this one clearly goes to 0. Okay, so all terms are bounded, all terms are converging. Necessarily this one is also converging. And we get, okay, I'm just using a bit Stocker notation here now. Okay, and then okay, and then this one. Okay, and then plus phi natural. And phi natural is which is exactly what we wanted to prove. Okay. Okay, so I'm almost done. Let me just make one final remark. So because now I did just for this course, for these lectures, I wrote down the system in Lagrangian coordinates. But somehow it's not very satisfactory. You kind of want to have an Eulerian formulation. So it's possible to show well-posedness for the Eulerian formulation in vorticity form. And so that's actually what we did in our paper. And you can show well-posedness for this equation and that the solution is really on this form. You can really show that there exists a flow, and this is really the only type of solution there is. Which is a bit more satisfactory. But so as I mentioned, rough path PDEs, because this is now rough path PDEs, the theory is quite underdeveloped. And it's quite, I mean, and it's not difficult, but it becomes very technical. I think it would be far too technical to really present on this purely Eulerian formulation. So that's why I sort of decided to do everything in Lagrangian coordinates. Yes. Yeah, so I guess that's all I wanted to say. Yeah. Plus, if there's a union in India for mathematicians, I would like to make a complaint that I had to give 2 lectures in one day. It's exhausting. Somehow it's even worse for you because you had to listen to me for 3 hours. But okay, yeah. Okay, so now that's it. I'm done. Any questions, comments? Yeah, random, yeah. For any PD? I don't think so. That would be surprising. For many you can actually, right? That's sort of this. If you don't care about regularity whatsoever, for a huge class of fluid equations, you can do this, and it is building on this sort of what's called geometric hydrodynamics. But I mean, I shouldn't say yes because I don't know. But I think for a large class of functions, you can write down some type of Lagrangian coordinates. Oh, Mario, what would you say? What's your gut feeling on this? Any fluid, you can write down the Lagrangian formulation.
I think it might be way more.
No, exactly. And I mean, you only need to go to 3D Euler to see that it's not as easy as here at all. Yeah.
That's one thing. Sometimes the geometrical formulation people consider not just position, but position and velocity.
Yeah. Yeah. Sure, sure. Yeah, but I mean also already in the 3-dimensional Euler case, right? Already here, because the vorticity formulation that we have here, that's a very nice, oh, no, it's actually here, it's a very nice transport equation. But already in 3D, this breaks down. It's a different equation. You have also multiplicative, what are called stretching terms, you know, for 3D. And then to write down a Lagrangian formulation, I don't know. I mean, you don't get this nice closed formula, then that's it.